interesting that happens. So here we want to sketch and label its image after horizontal compression by a factor of a half and then a translation of 3 units. The reason I'm doing both this example and the one off to the side is this one has to do with horizontal stuff, and we're going to write a special note about horizontal ones after this right at the bottom of the page. So you don't have to really write anything down because it's already there. If we write this in function notation, we have a horizontal compression of a half, then a translation of 3 units to the left. The way that we would write that, everything would be inside the function because it's all horizontal. The compression by a factor of a half will show up the opposite. So it'll be a reciprocal. It'll be 2 over 1, or just 2. And then the 3 units to the left will be an x plus 3. So we write it as if the 2 has been factored out. We don't write it even though you might be tempted to this way. Because these look different, and your gut probably would say this way first. And this is one of those situations where if you go with your gut, you're going to be wrong. Because you'd say, well, I know that this is a half, and to move 3 to the left, I need a plus 3. But if you check it with what is actually happening, that won't move it 3 to the left. It'll only move it 1.5 to the left. Okay? Because when I distribute this one, I'll get 2x plus 6. Now the reason for that is that, again, minus 3 is what would make this 0. And we looked at ways that keep it at 0 before. But if I plug in minus 3 here for x, it doesn't keep it at 0. So that does need to be factored out. When you're writing 2 sets of brackets, some people like square brackets for the first and round to differentiate between the 2 sets of brackets so you know which bracket goes with which. When I'm writing my notes, I like to make my first set big, and then if I have another bracket inside, I make it a little bit smaller just so that I can visualize it better, what goes with what. So this is how you would write the equation. And then what you would do is, if I deal with the compression, because working from left to right, I would deal with that first. I'll just draw that with a dotted line. Horizontal compression, this point would go to there, this point would go to there, this point would remain unchanged, and this point would go to -2. All my x coordinates have been multiplied by a half. And you have that graph on yours as well, right? They've drawn it in a solid line. If I was showing my work, I would draw it as a dotted line just to show I'm not done yet. That's just part of my work. Now, when I do my final graph, which I'll do in blue, I'm going to move it 3 to the left. So this point goes to here. This point goes to there. 1, 2, 3. This point goes to there. And we end up with our final graph. So at the bottom of your page, because we did this one with horizontal things, this is what I'd like you to write. Special note. When you have a horizontal, and it could be a horizontal stretch or compression or reflection, even if it's just a negative sign out in front, with a horizontal translation, you must write it in factored form. Yes. Yes, I'll just slide it up. This is the one that's correct. If it was 2x plus 6, it would be fine. Yeah. So if you had this equation in the right form but not factored, I mean in the right equation, it would start by looking like this, 2x plus 6. But before you could say which way it moves, left or right, you would have to change this by factoring out the 2 to look like this. And then you would say, since I took a 2 out of the 2x and a 2 out of the 6, I would get 2 times x plus 3. And now I could say, you multiply x by half and move it 3 to the left. Yes. Did my last point not go over 3? Oh, I used the red graph instead of the green one. Thank you. Nice. Appreciate that. I mean, these go on YouTube, so my reputations just would have gone totally into the gutters. Lost subscribers, man. There we go. That looks better. Whew. Yeah. Everybody get the stuff at the bottom. I'll slide it back down. Okay, let's just, I'm just going to, this green one, I'm going to change the color of it to blue because it is the blue one as far as color coding goes. Okay. Whenever you're moving something over, okay, a key thing to look at is where are the zeros? Where is it equal to 0? And when a function is equal to 0, that's when you plug in, you have to find the x value that would make it equal to 0. So in this case, if I plugged in -6, thinking it should be 6 to the left, I'm not going to get a 0 inside here like I did to begin with. But if I plug in -3 into either of these, that's what keeps it at 0. So this will be easier to see if I actually use an example that you can, like an x squared example that you know. Okay? So we're going to go to our graphing calculator and see this again with a parabola. So on my graphing calculator, I'm going to start by just graphing my parabola, x squared. So there it is, my blue graph. Yeah. And now what we're going to look at is I'm going to write in brackets 2x plus 6 bracket squared. So this should be a horizontal compression of a half. And now we're going to see that it does only move it 3 to the left, not 6 to the left when I go to graph it. So we can see that it's been compressed, that it's narrower. Okay? And the key point that I want you to see here is that this point, which was 0, 0, changed to -3, 0. It didn't change to -6, 0. Because what is it, when we look at our equations again, what is it that would make the inside still be 0? It would have to be -3. So instead, whenever we have something that looks like this, which is a horizontal compression and a horizontal translation, we will, before we graph it, rewrite it with the 2 factored out. So if I take a 2 out of both of those, I'll get another set of brackets, x plus 3 bracket, bracket squared. All I'm doing is factoring the 2 out of those 2 terms. It will cause some problems here.
Would it just square the x plus 3?
Yeah, it would just square the x plus 3 and not square the 2. So you need both sets of brackets. And now when I graph this, I notice that that graph is exactly the same. See it color over the red one. So it's the same thing. So this is a very important thing that will catch, you'll get caught on over and over again. This special note. Oops. There we go. That when you have a horizontal stretch and compression, you must write it in factored form. This one off to the side just has vertical stuff. No problems with vertical stuff. You don't have to worry about factoring at all with the vertical one. We've got a graph of g of x. We want a vertical compression of 1/3 and then a translation of 2 units up. That 1/3 would be outside of the function. The 2 would be outside of the function. And because it's all vertical stuff, it's exactly as you see it in the question. The 1/3 compression is a 1/3. Up to is plus 2. So again, horizontal stuff is opposite. You got the reciprocal, and you've got the opposite for left and right. Vertical stuff is just as you see it. So now if we take all of our points, and again, I'll do the first thing, 1/3, 1/3, 1/3, and 1/3, and connect the dots. That's doing the vertical compression first. And then finally, we're going to move it up 2. And I'm using all the green points this time. And there would be our final graph. Now, if you had a lot of transformations to do, then you get a lot of dotted things all over your graph, and you can see you might get things mixed up a little bit. The way that we would show the work for this with points is to start by having the points that we had originally on our red graph, which we have -5, 3. We have -2, -3, 1, 0, and 4, 6. These are the 4 key points on our original graph. Yes? Yes, because we don't know the actual equation of this red one. So when we're writing our function, we have to make reference that g of x was the original graph. And then we need the 1/3 and the 2. If you forget the g, that just makes a line that's y equals mx plus b. And this is definitely not just one straight line.
You have the G or the F or whatever letter in there for
when it's not a regular graph. This is writing it in the function notation. So when you have a function in there, what you're doing is you're referencing the function you were given originally and saying how that original function was changed. When we write it in the explicit notation, like we did, just to go back to the beginning here, this was explicit notation. Okay, there's no function here because we're saying that the square root is telling us what the original function was. Okay? Do you want me to write both of these in function notation as well? If you didn't know that the red one was square root of x, and they just told you that the red one was f of x. It might not be the square root of x. Then you would write this like this. Y equals, and I know that I have 3 to the left and 2 down. That would be writing it in function notation. The explicit notation says I know the function was a square root. So I can write the square root because I know that was the function. But in function notation, this is saying maybe I don't know the equation of the function, so I can't say that. This is just describing what's happening to it with any function that you could have had to begin with, even if you don't know the name of it. This one, if this was g of x, we would say, well, all we're doing is we're taking our original function and multiplying it by half. That's how you'd write it in function notation. So this is, I mean, it takes practice, and I'll keep asking about it. I'll keep showing and describing it again, and all of a sudden you'll see the connection, and it will connect. It'll click. It'll be good. Okay, so we were looking at this. Another way to do this one, we've done it with the points, is to label 4 key points to start with. Yes? The letters are just random. Usually they start with F for function because it starts with F. And then if you have a couple of them, then they go to G next, then H and whatnot. But yeah, the letters for a function are just random. So going from left to right, we have a vertical compression first, and then a vertical translation. Your vertical compression, to show your work, would say that you would multiply your y coordinates by 1/3, and that would take these points and you would just take all of your y coordinates and multiply them by 1/3. Then your vertical translation, do that one in black. This means up to, and then we would get -5, 3, -2, +1, 1, 2, and 4, 4. If you did this, what you would do is you would take those final points in black, plot them on your graph, connect the dots the same way, and you would get the same graph without having to draw the green graph in between. For this one, I think drawing the one-step graph in between on the graph isn't so bad. But like we saw in the Construct the Understanding, if you had to do like 6 of those graphs, a bunch of them, you might start getting annoyed. So then the points system might be quicker. So you can choose which method you would like to do on a question like this. And for practice, above this one you can write 4, 5, and 6. Some people just write the question numbers above the numbers so that you can reference it later. I see some of you turn to it and highlight them. You can do either way.